In question 4, you're asked to compute the impact speed of a body released from a known height, 800 kilometers, neglecting the effects of atmospheric drag, so only due to the force of gravity. But in part A you assume that there's a constant gravity acting, whereas in part B you account for the variation of gravity with altitude. Now, it's a good idea to think in terms of what the answer should be before you attempt the question, and given that if you assume a constant gravity, then at the beginning it's going to be subject to a larger acceleration than it would otherwise be subject to, because of course as you move away from the centre of Earth the gravity is decreasing. For part A, you would expect it then to arrive at the surface of Earth with a higher velocity, because it starts with a greater acceleration, therefore it's going to reach a greater velocity. When you actually take into account the variation of gravitational acceleration with height, then by the time it gets to h, it's going to have a lower acceleration to start with, which means it's going to be speeding up that little bit slower, which means that by the time it reaches the Earth's surface, it's going to be slightly less. So as we can see from the answer, here the impact velocity for part B is somewhat less than it is for part A. So for part A, we apply the constant acceleration equations. We're not concerned about time, so we have v squared is equal to u squared plus 2as. U squared is 0 because we're starting from rest, therefore it's 2 times 9.81, the constant gravity, times the height, being sure to convert into meters. Then the impact speed can be found to be, as shown, 3,960 meters per second. Then when we vary the acceleration, we have to come up with the functional dependence of acceleration with height. And the way you do this is by looking at the equation for gravity itself, universal gravity formula, and you've got it here. You've got the force of gravity at the surface of Earth is gravitational constant times the mass of Earth divided by the radius of Earth, or the distance from the centre to the surface of Earth squared, times by the mass of the object. And of course, all of this is equal to g naught, so that this can be rewritten as m times g naught. Now, in the situation where you're no longer at the surface of Earth and you have instead a separation r, that changes. So you could just say straight away that the force is equal to, or the acceleration r is equal to g times me divided by r squared, because you divide by m here and you divide by m on this side and on this side. But in order to keep it in terms of re, the Earth radius, we equate them. So what we say here is that by eliminating the gravitational parameter g and mass of Earth and the mass of the object, we can say that Fr times r squared is equal to F0 times Re squared, which is what this represents. It's just representing the conservation. If the radius goes up, then the force is going to go down. So rewriting this, we're able to put this in terms of a force for the gravity between an object mass m in the centre of Earth as a function of the gravity at the surface, and the function of the radius of Earth and the separation of the object from the centre of the Earth. This then divided by m gives you this expression, which is exactly the same as this. This is the same, it's just a different way to write it. One that will be convenient when we go through the integral. So, next step is to look at this and say, well, this has a functional dependence of r, or in kinematics this is displacement. So we need to identify the equation we're going to use is A times dr is equal to v times dv. And remember, this comes from the observation that v is equal to ds, or dr dt, and A is equal to dv by dt. And if you eliminate dt, you get the equation here. So using this, we make our integral, velocity on the left hand side, and 1 over r squared on the right hand side, where g0 and r squared are re squared are constant, so they go outside. And then you're left with, you integrate the left hand side to get half v1 squared, and integrate the right hand side, minus g0 r e squared. The integral of 1 over r squared is 1 over r negative. And then doing that for the initial and the final conditions, so going from the starting point, so the RE plus H to RE means that by substituting in the minus sign here, you get eventually 1 over RE minus 1 over RE plus H, and this can be simplified by looking at the common factor of the denominators. And finally, this can all be rearranged to give the final expression for V as a function of Earth radius and height away from the Earth's surface as follows. And we can see this is somewhat lower than it is in the case for if we assume the acceleration to be constant.